we saw the definition of a stationary distribution, of irreducibility, and of aperiodicity for Markov chains. And in this video, we'll take a look at some simple examples to illustrate these concepts. So first, let me make a remark here. When I defined aperiodicity, I only did it for irreducible Markov chains, and I did that because I was going to use a slightly different definition of aperiodicity that was simpler, but I turned out actually I ended up using the general definition, and so this holds actually even for Markov chains that are not irreducible. This is the same definition. Okay, so that was just a small generalization. And now let's look at some simple Markov chains. So first, let's take a super simple example, maybe the simplest possible thing. We'll just take two states. So let's draw the picture here. We have state 1, we have state 2, and we have some transition probabilities between each possible pair. So let's choose some transition probabilities. Let's say it goes from 1 to 2 with probability 0.2, and 1 to 1 with probability 0.8, 2 to 2 with probability 0.2, and 2 to 1 with probability 0.8. And let's call these, just to make it a slightly more general, let's call this Q and this P. And so then this turns out to also be Q. It's not always, these are not always going to be equal, but in this case they are. And this is P. So in general, we could have any P and Q that are non-negative and sum to 1 on this simple little diagram here. So what's the transition matrix? Let's write down the transition matrix. I'll sort of annotate the rows and columns here so we can mentally keep track of what's going on. So the first entry is the probability of going from 1 to 1. So that's this one. So that's P. And then this is the probability of 1 to 2. 1 to 2 is Q. Probability of going from 2 to 1. 2 to 1 is P. And 2 to 2 is Q. So we have our nice simple little transition matrix here. And it is a stochastic matrix, as it always must be. It's non-negative, and the rows sum to 1. So it's a stochastic matrix. And let's think about these properties. So we defined these properties, and let's see if they hold for this Markov chain. So let's think about irreducibility. Irreducibility says that for any pair of states, there exists some time for which we can get to, so if states are A and B, we can get to state B starting from state A with positive probability. So we're at state B at time t with some positive probability starting from state A. So this condition, actually, I sort of drew the picture here, the intuition, and in fact, you can prove, it's not hard to prove, that this is positive if and only if there exists a path x0, x1, x2, and so on, up to xt, a sequence of states that has positive probability. So if there exists at least, so this is true if and only if there exists at least one sequence of states that has positive probability, in the sense that when you multiply together the sequence of transition probabilities, then that product is positive. So multiply together the probability of going from x0 to x1 times the probability of going from x1 to x2, and so on. All those entries of the transition matrix. So we can check that very easily in this case. We only had two states, so to go from, say, 1 to 2, well, that's clearly we can do that with positive probability with just with Q, as well. That's as long as Q is positive. So in our little example here it is. And so it's irreducible as long as P and Q are strictly positive. If Q was 0, say, then we couldn't get from 1 to 2, right? We would just be stuck here at 1 for infinite time. And likewise, if Q, or rather if P was 0, then we would just be stuck at, we couldn't get from 2 to 1. So it's irreducible under those conditions. And what about aperiodicity? Is it aperiodic? Well, let's think about what aperiodic meant. Aperiodic was that the greatest common divisor of this set of times at which we can return to state A, starting from state A, with positive probability, the greatest common divisor, that was 1. And we said that that was equivalent to this set of times, which we called RA, being contained only in the set of multiples M1, only in all the integers. It's always contained in M1, and if it's only contained in M1, if it's not contained in M2, M3, or any of these others, M4, and so on, then this condition is true. So one easy way to check this, so here's a little trick that you can use to check aperiodicity. A trick you can use is that if this set RA contains 2 consecutive times, like in this situation, 2, 3, then this condition is satisfied. Then the GCD is 1. And the reason for that is just that, well, say, if this number, if this the first number is a multiple of k, then this one, and k is greater than 1, then this one can't be a multiple of k, and vice versa. If this one was a multiple of k and k is greater than 1, then this one can't either. And so therefore, if there's 2 consecutive times with positive that are both in this set, then the GCD is 1. So that's a little trick you can use. And let's check that on our little example here. So for state 1, we can, if we start out at time 0 at state 1, then time 1, we can also be in state 1 with positive probability. So we can return to state 1 at these 2 consecutive times, or you could say 1 and 2, these 2 consecutive times, and therefore that this aperiodicity is satisfied for this one, and the same thing for 2. You can return to 2, starting at 2 at time 0, you can return to 2 at time 1. So these are 2 consecutive times that are both in that set, R2 in this case. So aperiodicity is satisfied here, and so it's satisfied for all the states. And that was under the assumption that P and Q were strictly positive. We were sort of assuming that when I was saying that. If it was not, if Q was 0, then, you couldn't return to Q. And then it would not be aperiodic because the only time in this set, so if Q was 0, then you could not, so starting at 2, you could only go to 1, and you couldn't get back to 2 because Q was 0 here. So 0 would be the only element in this set R2, and that would be contained in all of these guys. So the greatest common divisor would be, it would be like infinity or something, but it wouldn't be 1, certainly, because every integer would divide 0. Okay, so it's irreducible and aperiodic under these positivity conditions, and let's check if it has a stationary distribution. So for a stationary distribution, we need to find some PMF pi. Let's remind ourselves the definition. Stationary distribution is a PMF pi on this set of states that satisfies this property, pi t equals pi, which is represented by these equations. So we just need to find this vector pi, and it turns out it's pretty easy to check that this is satisfied. This equation is solved by the vector pq. So let's check that. If we multiply pi t here, we think of it as thinking of it as a row vector. multiply it, then we get, multiply times the first column, we get the p factors out, and p plus q is 1. So we just get p, multiply times the second column, the q factors out, p plus q is 1 again, and we get q. So we just get back pi, pq, and so this identity is satisfied. So it does have a stationary distribution. So all three properties are satisfied, and therefore, for this simple example, then the ergodic theorem applies, and we get all those nice sort of asymptotic guarantees about the behavior, the limiting behavior of the the distribution of a random variables in the Markov chain, or if you were to take the sample mean of some function of the values, all those those guarantees that we had in the ergodic theorem. Okay, so one other thing I would like to mention here is that for aperiodicity, I told you one little trick you can use, which is if you have the two consecutive times. Another trick you can use, which turns out to be very, very handy when you have a larger set of states, is that aperiodicity only needs to be checked for one of the states when it's irreducible. So here, when we have an irreducible Markov chain, then this property holds for all states if it holds for at least one of those states. So if you can find one, so if there exists some a in X for which this holds, then in fact it holds for all a in X when it's an irreducible chain. So irreducibility gives you that nice sort of very, very, very handy way to more easily check aperiodicity. Okay, so that was a first super simple example of a Markov chain, and next let's take a look at a little bit more interesting one. We'll look at a couple more states and get to see some more interesting behavior, but I'm going to run out of time in this video, so let me stop there, and we'll come back and we'll look at some more examples.